Hello everybody and welcome to my sampling distribution video regarding the sampling mean and the sampling proportion. Just want to say that this information that's in this video and in this chapter is very important and that it will move forward for our inferential statistics. So please, whatever you do, make sure that you fully understand all the material in regarding the sampling distribution and the previous chapter regarding the normal distribution, as this video will also depend on the normal distribution. So without further ado, let me provide some introductory comments. So the first thing is regarding the mean. I'm going to go for the mean first. We'll do p hat at the latter part of this video. The idea is, suppose that we have a population and we're interested in something regarding this population. But we will also assume that this population has some true mean and some true standard deviation. Now in practice, we don't know this true mean and we don't know this true standard deviation of the population. When we move further in the course, we will talk about estimation, and we will try to get a hold regarding the mean of the distribution. But suppose that we're going to go out and in our population we decide we're going to choose some sample size, say n. So moving forward, n is always the same. So if you need a number, let's just say sample size 30. And based upon our sample size of 30, we can go out and we can compute this x bar. Now let's just observe that this x bar, once we have it computed, we can ask this question, and that is x bar exactly the same as the population mean? And in all reality and all sincerity, probably these two are not exactly the same. But one of the things we may be interested in knowing is, are they relatively close? And that is something that we would like to have happen. And we will investigate this in a little bit. So I could go out and throw all the people from the first sample back into the population, resample size n, and I can compute x bar 2. And let's just note that we can ask the same questions, and that is x bar 2 exactly the same as x bar 1? And probably more than likely it is not. And x bar 2 the same as the population mean? And again, probably not, but could they be similar? And that is something we would hope that would happen. Suppose we go out and do it the third time. So again, I have this third population. I throw all the people back in from sample 2. I draw sample 3 of size n. I compute x bar 3, and again observe that x bar 3 is probably going to be different than x bars 1 and 2, and again probably going to be different than the sample mean. Now suppose that we do this, say, I don't know, 100 times. Let's just observe that all of those x bars are all different numbers. All right, they're all different. But again, we would kind of hope that there are kind of hunkered around or maybe close to the population mu. But let's come back to this all 100 different x bars and let us ask and answer this question. Since all the sample means x bar 1 to x bar 100 are different, then this means that the sample mean x bar is a blank blank. Can you take a moment and think about that? Right? If you had to come up with an answer and say this was a 100-point answer, extra credit, what would you say? We have 100 different x bars. We have 100 different numerical values for these x bars. Well, that means that x bar is a random variable, okay? Since all of these are different, x bar now is a random variable. And since x bar is a random variable, then that means that there is a probability distribution associated with this random variable x bar. And not only is there a probability distribution associated with x bar, but there's also two parameters. Now, we've had you already in the past talk about two probability distributions, and that is the binomial distribution and the normal distribution. And let's just recall that the binomial distribution is fully characterized if you know n, the number of trials, and p, the probability of a success. The next distribution that we talked about was the normal distribution. And the normal distribution is fully characterized if you know mu and if you know the standard deviation sigma. So let's take a look now. The sampling distribution, again, in general, a sampling distribution, notice this, of a statistic is a probability distribution for all possible values of the statistic computing from a sample size n. So the idea is each time we do a sample, it's going to remain fixed at a sample size n. Because if you change n, believe it or not, as we will see, the distribution properties will change. And I would like to come back to this statistic. So each statistic that we have computed, x bar, which we're getting ready to investigate, sigma, our s squared, the sample mean, the sample standard deviation, and the sample variance are both statistics, and they have a probability distribution associated with them, as well as the median. The sampling distribution of the sample mean x bar is the probability distribution of all possible values of the random variable x bar computed from the sample size n from a population with a mean mu and a standard deviation sigma. So this is what we would like to further investigate as we move forward with our video. So this concludes the introduction regarding sampling distributions for statistics. All right, so to get started with the sample mean, we're going to take a look at two parts. Part one, we're going to assume that the population is normally distributed. And then in part two, we will take a look at when the population is not normally distributed. So we are going to assume, and what we're going to go after is the average age of students at some college or community college. And what we're going to do is survey 10 students and ask them their age. And we're going to repeat this survey 100 times. Now in practice, we don't get the 100 times. You just get the one time. And that is it. We are going to furthermore assume that the population is normally distributed and that it has a mean of 25 and a standard deviation of 3 years. So I performed a sample, a simulation using some statistical software, and these first 10 columns are the ages of 10 different people, and this last column right here is the x bars. So notice that, and I've repeated this, well, this is just a snapshot. These are the first 14. So the first 14 rows are a sample of size 10, and then this last column right here are the x bars. So here is my 100 x bars, and if you go back to the intro, this is one of those white circles that we were taking a look at. So what I'll do now is I'm going to focus on this last column of these x bars and use some of the stuff that we've talked about, and I'm going to introduce a new piece that's really simple to take a peek at. So I constructed a histogram of these x bars, and notice that this histogram does appear to be approximately bell-shaped, and bell-shaped or approximate bell-shaped distribution should start ringing normality to us. And let's just note that we said that we had a mean, that we did the simulation with a mean of 25 and a standard deviation of 3. So So a couple of things I'd like to point out is notice that the center of this distribution does appear to be right at about 25. All right, and notice that over here that the mean of all those x bars is 25.06, and notice that that is really close to this sample mean. Also, let's observe that the standard deviation of those 100 x bars is 1.166, and notice an only comment I want to make is that it is smaller than the population standard deviation. This next plot on the right is called a normal probability plot. Now, we did not have you take a look at assessing normality, but this kind of comes into play. And the idea is that if I do this normal probability plot and the dots, the 100x bars, appear to fall on a line, then I can conclude that there is normality, or at least approximate normality, of the data set. And because this plot on the right-hand side does pretty much fall on a straight line, I can come to the conclusion that visually speaking, and there's other tests that we can do, is that this distribution is coming from at least an approximate normal distribution. So just some quick observations that we have discussed is that we noticed that the histogram was bell-shaped. We noticed that the center of the distribution is similar to the population center. And we noticed that the standard deviation of the x bars is smaller than the population standard deviation. And then finally, we observed that the normal probability plot shows normality of the x bars. So this leads us to a conclusion, and that is that when the population is normally distributed, or what is also referred to as the parent population is normally distributed, and it has some mu, maybe we know it, maybe we don't, some sigma, again, maybe you know it, maybe you don't, then here is the fact number one. Fact number one is that x bar is normally distributed. Second, we need the parameters to the normal distribution, and we have seen that the mean of x bar, that's what this symbol is right here. So every time you see that, this is the mean of x bar is equal to the population mean. Notice there's no subscript. So when there's no subscript, this always refers to the population mean. Whenever there is a subscript, then it's the mean of whatever that subscript is. And then we also note that the standard deviation of x bar, I didn't go into this, but let's just note that we said it was smaller than the population standard deviation. And here is the relationship, that is that the standard deviation of x bar is the population standard deviation divided by root n. Notice two things. Whenever we take the standard deviation and we divide it by a number bigger than 1, that makes the ratio smaller. And notice that as n gets bigger, that the ratio tends to get smaller. So putting everything together, so if you had to remember one thing that I have talked about so far in the last 14 minutes to include the introduction, is that x bar is guaranteed to be normal, and its parameters is mu sigma over root n. That is something I want you to remember. All right, moving to part 2 is what happens when we do not have normal data, or non-normal data, if you will. So let's take a look at this one. Suppose that we work for the Department of Fish and Wildlife or whatever, and we're interested in the average length of trout at the Cherry Creek Reservoir. So on Saturday, we allow 100 people, or 100 children to go out and do a little catch and release, and we are going to allow these children to catch some fish. Now this does say 20, this should be 5 for right now. So we're going to allow them to catch 5 fish. So again, I did a simulation, and here is a snapshot just to note that here are the lengths of the first 5 fish. This was a catch and release, by the way. So we have to have that release each time we go from one sample to the next sample. And then again, here is our X bars. So just like we did before, I'll do a histogram, and notice that the histogram appears to be bell-shaped approximately. And again, we take a look at the center of the distribution, and I think we can pretty much tell that this is guesstimate about 9. And so if we come right over here, let's just observe that the mean is 8.92 and that the standard deviation is 1.243. And again, notice that if we take a look at this probability plot, I think that we can see that these dots, these 100 x bars, pretty much fall on a line. So it does appear that these are coming from a normal distribution. So again, our conclusions is that we have a bell-shaped distribution. This throws up a normality distribution or a normal distribution. Our probability plot shows normality. We found that the center is about 9, all right? And we had a spread of the distribution. We'll observe something here about that spread in just a moment. So let's repeat this one. So this one I'm going to repeat and allow the kids to catch 20, a little 20 catch and release. So again, here are the 20 catches, and it's repeated 100 times. And unfortunately, I couldn't get the X bars on the screen, but over here is where the X bar is at. So again, taking a look at our distribution here, we can see that this is bell-shaped. So bell-shaped should bring normality. And again, look at the mean and look at the standard deviation. It did decrease from our previous bell-shaped distribution with sample size of 5. Let's take a look here. We do have, so to test for normality, it appears that we do have normality. And again, just to take a peek-see here, both of these appear to be centered at 9. But look at the spread. This one here has a spread of 1.243, and this one has a spread of 0.5624. So again, notice that as the sample size moved from 5 to 20, the standard deviation did get smaller. So again, for our 20, sample size of 20, we have bell-shaped distribution on our histogram, leads us towards normality. We do have normality, and the center and everything of this distribution appears to be centered at 9. I'll get into a little bit more of that in here in just a minute. And again, that the spread becomes smaller as the sample size increases. So this leads us to a very important theorem regarding non-normal data, and this is the central limit theorem, and this is going to pop up in the upcoming chapters. So this thing says that regardless of the shape of the underlying population, no matter what the distribution of the population is, the sampling distribution of X bar becomes approximately normal as the sample size n increases. So we get convergence to normality as the sample size n increases. And when the sample size gets large enough, we'll have really good, strong normality. And statisticians have agreed that when we talk about large sampling, this is normally, and I believe this is in the handouts as well, is when the sample size is 30 or bigger. Okay, so this is just kind of a common rule of thumb. It's not anything etched in stone and doesn't mean that this is an absolute that is going to remain true forever. So let's just take a look at the visualization. Here I have a normal distribution. We talked about this regarding part 1, and as the sample size gets bigger, we have convergence to a normal distribution. Here I have this J-shaped or skewed right distribution with a sample size of 2, and then a sample size, so sample size 10 and 100 of those, and do our histogram, and then a sample size of 30. Okay, we can see that as we move down and the sample size increases, that we get this convergence towards normality. Now this is referred to as a uniform distribution, and with the fish I did what's called a discrete uniform. So rather than having this, we would have just the dots, and I did mine from 5 to 8, 13. So notice that the middle between 5 to 13 is 9. You just add them up, divide by 2, and notice that this center remains at 9 all the way through. So the central limit theorem gives us approximate normality as the sample size increases. And the moral of the story is when the sample size is 30 or larger, you got really good approximations. So that's what our moral of the story part 2 is that no matter the distribution, all right, we're going to end up with normality. The center is going to be the same as the population mean. Again, if we knew the population mean. And notice the standard deviation again is the population standard deviation over root n. The moral of the story here, x bar is, and it's this word right here, approximately normal. Notice that when we had a normal population data set, we were guaranteed normality in part 1, and in part dos, or in part 2, this is approximate normality. All right, that's the difference between the two. And that concludes this part of our video. We'll be moving on here in just a second. All right, so I'd like to take a look at an example real quick on how we can apply all of this. So it says that the reading speed of second grade students is approximately normal with a mean of 90 words per minute and a standard deviation of 10 words per minute. So part A asks, what's the probability if we randomly select a student will read more than 95 words per minute? What is the probability that a random sample of 12 second grade students results in a mean reading rate of more than 95 words per minute? And part C asks, what is the probability that a random sample of 24 second grade student results in a mean reading rate of more than 95 words per minute? I just want you to take a moment and reread these. Just pause the video, reread these, because the phrasing of these questions is very important. All right, so let's take a look. Part A is just using our Chapter 7 techniques, or wherever your normal distribution is located. This is just a probability involving X. This one here, Part B, notice it's asking, what is the probability that a random sample of 12 second grade results in a, and is this keyword mean? So this is a probability involving X. This is a probability statement involving X bar. Notice that part C, what is the probability that a random sample of 24 second grade students results in a mean reading rate of more than 95? Part C is regarding X bar. All right. So now we have to determine, is this going to be a probability question involving X, or random variable X, or is this going to involve a probability question on our random variable X bar? All right, so for part A, this is just asking what is the probability that X is greater than 95. So using StatCrunch, all we have to do is go to StatCrunch and then go to calculators, normal, just like you saw in the previous videos. And all we have to do is fill in. Here's the mean is at 90. Here is 10 is the standard deviation. So what is the probability that X is greater than or equal to 95? Again, whether it's greater than 95 or greater than 95, greater or equal to 95, it doesn't matter. So notice that we come back and we get an answer of 0.3085, rounding to 4 decimal places. So part A was just a regular old normal distribution. So let's just notice that part A says, well, we have 12 second grade students. We want to know what's the probability that the mean reading rate. So this is a probability statement involving X bar. All right, so notice my probability statement is X probability that X bar is greater than or equal to 95. Now that means I have to come up with the distribution for X bar. And we know that the distribution for X bar is normal with a mean mu and a standard deviation sigma over root n. So in this case, we get normality, and mu, which is the mean of the population, is 90, but the standard deviation is sigma 10 over the square root of the sample size. And all I did was use my calculator to get a decimal approximation in order for me to use StatCrunch. So notice again, I do my StatCrunch, and the mean is going to be 90, except now I have to update this to 2.8868. And if you would, you can go ahead and verify my computation and let me know if this is not quite correct. And notice here we got a smaller probability. So here we got a probability of 0.416, 0.0416. Okay. And then finally for part C, it's asking what is the probability that the mean reading rates is greater than or equal to 95. But notice, because the sample size increased, the sample size changed, then that means that the distribution of X bar changed. So X bar is no longer distributed normal 90, 10 over root 12. It is now distributed normal 90, 10 over root 24, and this gave me a normal 90, 2.0412. Again, please feel free to double check me. And so when I did this, I just made the appropriate updates here and here. And notice that this probability is even smaller, 0.0072, rounding to 4 decimal places. All right, so this is an example of one of the ways that we can use the sampling distribution of X bar. All right, welcome to our last phase, and this one has to do with the sampling distribution for a sample proportion. This one is something we haven't really seen or talked about a whole lot. Okay, so I would like to take a moment and make a quick introductory comment regarding proportions and the sample proportion, this p hat. All right, so suppose that X, Y, and Z Political Consulting surveyed 1,012 registered voters between July 12th and August 3rd. It was found that 47% of the voters would vote for candidate A. Now, let's just observe that we went out and they asked 1,012 registered voters. Now, I'm thinking that if we're thinking of the state of Colorado and all the registered voters in the state of Colorado, we can pretty much think that there is a lot more than 1,012 registered voters. Even in the city of Denver proper itself, where I live, or in the city of Westminster, where you live, or the city of Lakewood or Commerce City, I think we can all agree that no matter where you're at right now, unless you're living in a very, very small town, that there is more than 1,012 registered voters. So one of the things that we can think of is that there is a true population proportion out there that would vote for candidate A. We just don't know what that is. So that goes back to the true population mean that we talked about earlier in the introduction component, where we found out that the population had some true mean and true standard deviation. Here, this is not a big stretch of the mind or the imagination that we can say, well, there should be more than 1,012 registered voters. And the idea is that this 47%, well, we would kind of hope that that 47% is pretty representative or pretty close to whatever that true proportion is. It's just that, as you found out in the last election, sometimes they're way off, and that's because a lot of people change their mind at the last second. So anyways, this 47% would be the p hat. So so the next thing that we would like to do is, how would we use this? So suppose that 50 registered voters are selected. What is the probability that 20 would vote for candidate A, at least 25 would vote for candidate A, or at most would vote for candidate A? All right, so this should look familiar. This was our binomial probability distribution. And again, earlier in this video, it was stated that a binomial distribution is fully characterized if you know n, the number of trials, and p, the probability of a success. So down here, this would be n, the number of trials, not this n here, okay? And then p would be our probability of a success. So once I know that, I can ask any probability question regarding this scenario that I wanted to ask. All right, so p hat then comes about by this little fraction guy here. So it's x over n, where this x denotes the number of individuals in the sample with some specified characteristic. So if I was looking for brown-haired people, if I was looking for blue-eyed people, if I were looking for Latino people, if I was looking for anything, all right? And n would be the total number that was sampled that I did in my sampling this case. So this is how p hat is computed. So it's just this little fraction if you ever have to compute this. So when we go out and do this, if we're taking a look for candidate A, so let's suppose you're on candidate A's team. So, we got a big election year coming up. So you can either take a look at the presidential, or you could take a look at the Colorado Senate race right now. And if you're on John Hickenlooper's camp, maybe you want to take a look at asking people, if the election were held today, would you vote for John Hickenlooper? And the idea is they either would say yes or they would say no. So if they would say yes, we would encode that as a 1. And if they encode that, or they stated 0, we would encode that as, if they said no, then we would encode it as a 0. So this is, I'm not going to go through the simulation, but I think this tells the same picture. And that is, notice that if I go out and I sample 10 people right here, all right, then notice that there is some true population proportion. We don't know what it is, but notice that we get this p hat, which is similar to our x bar. Again, I can go out and ask another 10 people, and all you got to do is just add these up and divide by 10, and it gives us this 0.7. So coming to this third row, notice it's 1, 2, 3, 4, 5, 6, 7, 8. 8 divided by 10 is 0.8, and so forth. Okay, so this would be kind of the simulation that was going on, but the idea here is that we would do this maybe 100 times, and we end up with this p hat. And again, now we'll just work with the p hats. So the idea now is, notice that the sampling over here, we have a sample of size 10, and here they generated this with a p, a true proportion of 0.76. So notice that we get this bell-shaped, or at least approximate bell-shaped distribution, and notice it appears to be centered right about here. All right, so we can repeat the experiment, and instead of having 10 columns and 100 rows, we'll get 25 columns and 100 rows with the same one here. And notice again, it's centered about right here at this 0.76, okay? And it's still bell-shaped. And then notice if we increase to 50 columns and 100 rows, compute our p hats, notice we get something that looks like this. So notice that these all appear to be centered at 0.76 across the board for the 3 different sample sizes, okay? And notice that the spread, notice that the width of this histogram is getting smaller as the sample size increases. So again, we're having apparently something similar going on with our population proportion that we had going on with the mean. Observation number 1, it appears that these are all centered at the same population proportion, and as the sample size increases, notice that the spread of each of these histograms decreases. So the moral of the story in the sampling distribution for p hat says that p hat, well, no surprise, is approximately normal. Now, just like we had talked about the central limit theorem, we need some sort of justification, or how does this work sort of rule of thumb. And this works provided that np 1 minus p is bigger than 10. If this condition is met, this is considered that large sample size case that we had with n greater than or equal to 30 back with the central limit theorem. So the mean of the sampling distribution for p hat, mu sub p hat, is the same as the population proportion, which we saw with all three of those histograms. And the standard deviation, well, we'll just go ahead and give this to you, is p 1 minus p divided by n. The moral of the story is, as n gets bigger, this fraction gets smaller. Okay, and we saw that relationship. So, moral of the story, part 3, is that p hat is approximately normally distributed with these parameters right here. Okay, so what I'd like for you to be able to do, because we're going to use this fact, and I cannot stress this enough for you guys, we will use this fact in the next coming chapters. All three of our inferential statistics chapters, 9, 10, and 11, we will use this information. So you need to know it now. And all I'm asking you to do is to describe the sampling distribution for p hat. So again, coming back here, it was found, this is our familiar political consulting. All right, so we would like to characterize the sampling distribution for p hat. So here, notice our condition is met, and p 1 minus p is about 252, okay, which is greater than 10, so it works. So that means that our sampling distribution for p hat is approximately normal, all right, with 0.47 as its mean and 0.0157 for its standard deviation. All right, I hope this little video tutorial helped you out regarding the sampling distributions. And at the end of the day, I need you to remember part 1 states that if the population is normal, then X bar is guaranteed to be normal. Part 2 says no matter the distribution, based on the central limit theorem, X bar is approximately normally distributed. And regarding proportions, our sample is going to consist of a bunch of ones and zeros. And at the end of the day, p hat is approximately normal as well with those associated parameters. And for p hat, as long as this condition np 1 minus p is greater than or equal to 10, which puts us what we would call a large sample case. And right now, that concludes my video.